Hello everyone, hope you are doing well. Welcome to the online platform Civil Techno Bricks. Guys, here we will tune for the instantaneous decoding of the conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today, we will go through the core concepts related to the digital elevation model and terrain analysis. Digital elevation model represents the earth's surface elevation in digital form. The objective is to analyze the terrain characteristics. So a digital elevation model is a digital representation of the continuous variation of relief over space. It transforms physical geography into actionable engineering data. The derivatives includes that the slope, aspect and contour maps with the 3D representation of terrain. The digital elevation model and the various ways we represent the terrain in GIS environment. So in civil engineering, the Z coordinate, that is the elevation, which is just as important as the horizontal position. Here we explore the mathematical and data structure used to model the Earth's surface, specifically comparing raster-based digital elevation models with vector-based triangulated irregular networks, that is TIN. So the 2.5D concept, which is the unlike full 3D model, standard digital elevation models are single valued surfaces where each xy location has exactly related with the z elevation. So xy, that is 2, and z elevation will be the zero point 0.5, that is 2.5D concept. So what is the structure? The structure represents topographic features or surfaces such as fields of connected z values, that is with reference to the elevation. So each and every coordinate which have the xy coordinate, and that coordinate is related to the z, that is elevation. The digital elevation model, which is related to these two models, or we can say the trinity of surface models: digital surface model, DSM, digital terrain model, DTM. Digital surface model, which is the first written, that includes trees, rooftops and infrastructure on the earth surface, which is used for line of sight and telecommunication purpose. Digital terrain model, that is DTM, which is a bare earth where vegetation and structures are removed, and critical for only hydrology and flood modeling. We can use it on the basis of contours. Third one will be the canopy or height difference, that is the digital elevation model, which is the generic umbrella term for topographic height data. We can use the digital elevation model to study the constructed materials height or the natural trees and their height with reference to the digital surface model or terrain model. So digital elevation model, which is a quantitative representation of the earth's surface in digital form. It is a regular grid of cells where each cell is assigned a specific elevation value relative to a vertical datum like mean sea level. The digital elevation model is the digital equivalent of a topographic map, but which more powerful when it allows for automated calculations of volumes and drainage patterns. So we distinguish the digital elevation model from a digital surface model, which includes buildings and trees. As civil engineers, we usually prioritize the bare earth, that is digital elevation model, for study purpose. The raster data structure for terrain, that is the matrix approach of raster digital elevation model structure. So implicit topology and storage, which is the most important policy, where each and every raster image is considered as dividation of rows and column with reference to some digital number, and that is used with reference to the resolution pyramid and scalability from the source of image capture, that is aerial photogrammetry or the satellite image. So we have to divide that whole image capturing in the three level 1, which is a fine, that is for example 1 meter from the earth surface. Second level will be the medium, that is 30 meter, and third level will be the coarse, that is 90 meter. So with reference to that, each and every image captured will be increased in detail with reference to its size, with reference to its xy coordinates axis. So implicit topology is the earth is divided into a regular grid of square cells, that each cell is used to store the data based on some elevations each, and that elevation are the numerical values or attributes for each and every row and column address. That is R1, C1 will be the 10. What is the use of resolution here? Defined by cell size. For example, 30 meter versus 1 meter. Likewise. So the most common way to represent the elevation is through a raster data structure. In this model, the terrain is divided into a matrix of square cells, and the resolution of these cells are such as 30 meters or 1 meter, which determine the level of detailing. While raster digital elevation model are excellent for computational efficiency and area-wide modeling, they can struggle to represent abrupt changes in topography like cliffs or retaining walls which are constructed. For large-scale watershed detailing or modeling, a raster digital elevation model is usually the standard choice due to its simplicity and compatibility with satellite data. So resolution pyramid enhances the scalability of raster with reference to the elevation which are assigned based on some rows and columns, cells or grid cells. Adaptive geometry, that is the TIN model, that is Triangular Irregular Network model, which is a vector-based model representing terrain using triangles. The objective is to model complex surfaces accurately, where flat plain, low density, modern mountain ridge, high density. Means in mountainous region, their TIN model is more dense, where for flat terrain, the TIN model is low dense. It works by connecting irregularly spaced points into triangles. It provides high accuracy in representing terrain variation. So large amount of variation is noted in the mountainous region. That's why density is more. The applications of TEAN model includes earthwork calculation, terrain modeling, and construction planning. The TEAN is a vector-based alternative to the raster digital elevation model. Instead of this rigid grid, a TEAN uses a series of non-overlapping triangles to represent the terrain surface. The vertices of each triangle, that are the mass points with known x, y, and z coordinates, and they are connected by edges to form a continuous surface. For civil engineering point of view, TEAN are often superior to raster because they can incorporate break lines which are like the center line of a roadway or the edge of the canal, which provide a much more accurate model of man-made structures. So the points connected to form triangular facets, optimizing storage and accuracy, which will the actual structure of TEAN model with reference to the density. It may be high or it may be low. Triangulation and topology concept. The triangulation and topology concept, which is the creating a DEM where nodes are there. The nodes are nothing but the vertices which are having the x, y, z coordinates. Two nodes are connected by the edges, that are the lines connecting the nodes which define the slope and direction. Faces, this is the actual area enclosed in between the node and edges, that is the area of the triangle itself, which defines aspect and surface area. Likewise, we mark the triangulation procedure on the topographical surface or topography with reference to the continuity. Their triangular mosaic tiles ensures a continuous surface where every piece fits its neighbor with reference to the nodes, edges, and faces. So, what is the application of triangulation and topology concept, which is best for sharp breaks in slope, that is road cutting and river banks area. To build a TIN model, we use a mathematical process just called as a triangulation. This algorithm ensures that no mass point falls inside the circumcircle of any triangle in the network, which creating triangles. So each and every triangle must be equilateral. This minimizes interpolation errors and ensures a smooth representation of the terrain. When we use to import survey points from a total station into GIS or CAD software, this is the process that skins those points or sends those points into a solid surface. It is a gold standard for high precision site designing. Surface orientation, that is aspect calculation. The aspect calculation concept is depend on the actual slope or the gradient available with reference to the GIS data. where x, y and z coordinates are there based on the elevation. Aspect is the direction that maximizing the slope faces, or we can say that the azimuth. That aspect is noted with reference to the horizontal face, but the normal vector which will incline with reference to that aspect, and we can measure the angle of azimuth with reference to the base plane of that normal vector. Here the directions are given north, east. With reference to that, we can checking the elevation, which gives the aspect calculation. So calculation logic is defined and derived from the normal vector of the facet. So significance is that solar energy south facing versus north facing means the directions are given, or directions of north are of the solar energy radiations direction, where hydrology is the direction of runoff, that will be the actual flow path of the water with reference to topography. So surface orientation, which is most important type for choosing between the digital elevation model and a triangular irregular network, which depends on engineering objectives. Raster digital elevation models are data heavy but easy to process for regional analysis like flood modeling or regional planning. TEN are most efficient because they are use points in complex terrain and fewer points in a flat areas, saving storage space without losing details. For site engineer designing a built pad, precision of a TEN is required. A transportation engineer planning a regional corridor might rely on a raster digital elevation model for initial route selection. So that normal vector and aspect which is most important for the site selection, route planning and route mapping with reference to that aspect calculation. Visualizing relief, that is contour generation, which is the most important point based on the steep terrain or flat terrain like slope and aspect, which is the part of terrain analysis. Here the isolines connecting points of equal elevation are marked. So interpolation is most important to track the points with reference to the ground control points. For that, computer algorithms draw lines linearly between grid points. So most important challenge is that in clips, automatic contouring can become too dense. That is, index contours are used to simplify visualization. So here we are visualize the actual terrain or natural terrain with reference to the contour generation with equal elevation grids. So that terrain analysis, which is the most common output, are slope and aspect maps. Slope tells us the rate of change of elevation, that is steepness, which is critical for identifying areas prone to landslides or determining the maximum gradient of a new road. Aspect tells us the compass of direction, that is the slope faces. In urban planning, aspect is used to optimize solar gain for buildings or to predict snow melt patterns in colder climates, directly impacting storm drainage design. For hydrologic analysis or for the flow direction point of view, we can use that steepest descent rule, that is the drop of water will move to the neighbor with the steepest downward gradient, just like slope with reference to the natural terrain. So the terrain with reference to its slope, the actual rainfall is traveling in terms of runoff through it. So we have to mark the actual path of that or the direction of that runoff. So drainage network, which is the cell to cell connectivity, which defines the stream path, that streams will flow over the ground surface with reference to the digital terrain model is required, but not the digital surface model. So digital terrain model mark the direction of runoff. By analyzing the elevation differences between adjacent cells, just like 55, 50, 58, the GIS software can determine the flow direction, that is the path of a drop of water would take to travel through the landscape. We use the D8 algorithm, which assumes water flows to the steepest of its 8 neighbors, just like shown 50. The 8 neighbors of 50 are listed below. With reference to that, D8 algorithm is work for the same, and we can mark the activity of water flow. This is the first step is automatically delineating or designing for watershed, which are identifying the natural drainage paths that will inform us to mark the design of culvert or location of culvert below to the road surface or any railway line or any bridge design. For hydrological modeling, that is watershed delineation point of view, by calculating the flow direction for every pixel, we can determine the flow accumulation, a count of how many upstream pixels drain into a specific point. So process steps for the hydrologic modeling: first flow direction, then flow accumulation and delineation. So flow direction, determine direction for every cell based on steepest descent. Flow accumulation, which is the count how many cells flow into each cell, that is cumulative contribution. And delineation is the identify ridge lines, that is divergence, as boundaries connecting the outlet. So areas with high flow accumulation represent streams and rivers, while areas with low accumulation are shows the ridges. This allows engineers to automatically map out the drainage network of a site without manual surveying. In GIS, this is used to calculate the time of concentration and peak discharge for a catchment, which is the primary input for designing and marking the hydraulic structures. So the defined definition of watershed is the total area contributing flow to a specific outlet point. So what are the applications with reference to the engineering point of view? Here two conditions are there: highway planning and second one will be dam planning. With reference to the highway planning, we are civil engineers, we have to construct the highway on the flat terrain. We have to study first the natural terrain with reference to its irregular shape, and we have to perform the activity of cutting and filling with reference to the flat surface provided. So we have, for providing the flat terrain, cut and fill analysis balances the earthwork volume and its cost also. With reference to that, route optimization avoids excessive slopes so that large amount of flat terrain will be achieved. For dam planning point of view, we have to provide the huge amount of space to store the water. So digital terrain model calculate the storage capacity, that is volume, at specific water elevation levels. With reference to that, each and every coordinate mark with reference to its elevation so that we can calculate the actual volume of water will be stored with reference to the surface available. The last point, that is the terrain analysis workflow, which is nothing but a procedure where the digital elevation model transforms physical geography into actionable engineering data. For that purpose, we have to follow 5 steps: capture, model, differentiate, analyze, and apply. First step, which is based on the capturing, that is data capturing by using some lidar survey or by using some photogrammetry tool. We can also use the sensors technique for data capturing with reference to the resolutions. The whole data which is used as an input for the modeling, that is the raster data for the teen generation. The third step, where the comparison of digital surface model, digital elevation model or digital terrain model, which used to differentiate the actual ground control points with reference to the elevations, with reference to the slope, with reference to the aspect or any topographical characteristics. That differentiation must required to analyze the actual data with reference to some objectives, just like hydrological monitoring or some irrigation purpose. The slope, aspect and flow are analyzed with reference to some mathematical calculations, and at the end we have to take the engineering decision or we have to frame the policy. That application point of view, we to start the excavation method or to construct the site of dam or any roadway. That are the most important terrain analysis workflow which will be followed with reference to that digital elevation model for geographical data so that we get the actionable engineering outcome. Stay tuned guys. Happy learning.